Hello and welcome to the AI Engineering Podcast, your guide to the fast-moving world of building scalable and maintainable AI systems. Your host is Tobias Macy, and today I'm interviewing Philip Kiely about running open models in production. So, Philip, can you start by introducing yourself?
Hi, Tobias. Thanks so much for having me today. So my name's Philip. I work at a company called BaseTen, which does AI infrastructure for inference. And as part of that, I've learned a bunch about the challenges of bringing open source and custom models to production. So I'm really excited to have a conversation today about sort of the state of open models and the process of getting them to a place where you can, treat them as viable alternatives to closed models for building AI native products.
And do you remember how you first got started working in the ML and AI space?
Absolutely. So, in school, I went and got a CS degree, and I was not particularly adept at AI and ML stuff. I got a B minus in my statistics class and was much more of a traditional web developer. But after college, I got into technical writing and I joined BaseTen off of a cold email and said, hey, I'm good at writing. I'm pretty sure I can learn this ML stuff on the job. And that was before kind of the explosion of generative AI. This was almost 3 years ago at this point. So I had a great opportunity to just kind of learn on the job and pick up those AI engineering skills along the way.
And before we get too far into the operational aspects, one of the other nuances that has been going around a lot is what does it even mean for a model to be open? Open in what sense? Because there's been all of that pushback on the use of open source in the context of open models. And I'm wondering if you can just give your stance on how you think about that terminology.
That is a great question. I was actually doing a sales training last month and got to explain to a room full of salespeople what open source is and how these different definitions exist. And I think I called it a source of major nerd pedantry, as in there's a lot of very small distinctions that can be made here, but they're important. A truly open model is usually defined as open weights, open data, and open code. So you can see everything that went into it, you can see everything that went out of it, and you can see the process that got it there. From there, there's also stuff around commercial use restrictions. There's questions of sort of a copyleft model licensing strategy where in my view, a truly open model is something under an MIT or Apache license. But at the same time, I don't really feel the need to be super pure about it in day-to-day work. After all, I think the most influential open source model is Llama. It's not a particularly hot take to say that. And that's been released under a series of custom licenses. And credit to Meta, I think that they've been listening to the developer audience and removing restrictions in those licenses that don't make sense. Restrictions like, what you name fine-tuned models. Restrictions like how you can use model outputs to improve the quality of other models. So while, I think that the legal setup around open source models is going to be more of a minefield in the years to come than, say, the legal setup around open source sort of more traditional software. I do think that it's something worth navigating, because if we want companies, especially companies that aren't just giant, FANG type companies, to have the economic incentive to create awesome models and bring them to us as developers, then I think we have to accept that there's going to be some experimentation in terms of business model to figure out a sort of viable path forward, whether that's releasing certain models as open source and reserving the sort of pro versions of these models as proprietary, or whether it's, sets of use restrictions like we see with Meta. I just think that we're going to have to work as an industry to define something that both makes sense for developers and also makes sense for the companies that are spending, in many cases, millions and millions of dollars to bring these models to market, where they might only have a few weeks as the top dog before something else comes along.
And to my understanding, the only model that really fits that truly open designation are the Ulmo class models from the Allen Institute, but I haven't been keeping as close an eye, so I don't know if maybe there have been any other entrants that map to that.
There's a startup called Nomic that has released several models like that, text embedding models that I know of. I'm sure there have been others as well, where you get those open, open weights, open data, open code. But in many cases, you might get one or two out of the three. And I think that, given how quickly the space is moving and how quickly techniques from one model are getting integrated into others, that the while the sort of most pure definition of open source might not be followed 100% of the time, the sort of spirit of sharing all of this information and learning and building off of one another is definitely present in the industry today.
Now, getting into the operational aspects of actually building applications off of these models, running them in production, can you start by giving a bit of an overview about the main decision points that an individual or team has to work through before they even get to the point of actually running one of these systems?
Absolutely. I think this is a super important question and one that it's really easy to skip because you can just like play with the fun new toys and dive into the tech and not really think about why. But I think this has to start at the product level. So thinking about, are you building a AI native product? Are you building an AI feature into an existing product? Or did your boss say, hey, we need to have AI and we need to have it yesterday? And you're figuring out a way to kind of shoehorn it into someplace where it might not necessarily make sense. So if we're talking about though a AI native product, one which we kind of define as something that couldn't exist without AI. So for example, a phone calling platform where you can call up and speak to an AI agent, or maybe like a video editing platform that's going to automatically cut up videos for you. In these cases, you have to start looking at the model level. You have to look at proprietary versus open source models and see what models out there do what you need. It's also very possible that there just won't be a model that does what you need. So the question is, can you prototype? Can you use a existing model to kind of prove the product and the MVP, and then once you achieve some early traction, then start to fine tune and build custom models? Or are you going to go for more of a pure play where you are becoming a research lab and your product kind of is a model? So kind of figuring out where in that spectrum you and your team are operating is super important, because that's going to inform everything downstream. A model research lab bringing a custom model to market via an API is going to have an entirely different set of concerns and constraints than a traditional SaaS platform that's trying to build a talk to your data widget integration.
In terms of the 0 to 1 challenge of I have this idea and then moving to I have something that actually works, there are a lot of minute decisions that need to be made in that process, a lot of experimentation that needs to be done as far as playing with different models, playing with different prompts, etc. I'm curious what you see as the biggest maybe cliff that folks run into as far as being able to actually go from idea to working implementation, and some of the main drop off points where they decide to where they just throw up their hands in disgust and say I'm done with this doesn't work, I don't I'm going to go back to what I understand.
Absolutely. I think that the first big hurdle is just having a good sense of evaluations. You can pretty easily get vibes off of any model. I have, for example, this image model called Playground 2 that I love to use to make blog post images for every blog post I publish. And there have been new models that have come out with new and more advanced capabilities, Playground 2.5, all this sort of stuff that I've tried, and sure, they're better. But like off of vibes, I like Playground 2. It makes things that have a sort of aesthetic that I enjoy. So going from that kind of vibes based evaluation, which works fine for, hey, I'm just using this model to make header images for my blog posts, to a more rigorous and robustly defined set of capabilities that you need the model to have, and a way of sort of testing that is that's definitely a critical first step. Because if you can't be confident that the model actually does what you need it to, then you can't actually build an application around it. So it's the evals are what the evals are where I see the first big stumbling block.
You mentioned that model selection is one of the main decisions that can have the biggest impact on all of the downstream choices that have to be made. And what I have seen from my limited exposure to some of the product development that people go through is they say, hey, I'm going to go ahead and build some AI service. I'm going to go ahead and just use OpenAI GPT-4o or whatever the latest model is. And then they say, hey, it works great. Now I'm going to go to production with that, not even really thinking about the fact that it only works because the model is so massive. And that also is going to increase the latency, the cost, versus starting with, I want to prove out this idea. How small of a model can I get away with before moving to the bigger models? And I'm curious what you see as some of the general approach that people take on either end of that spectrum.
To be honest, I think that starting with the biggest, best model is a great approach for prototyping, because you want to, in that prototyping phase, eliminate as much uncertainty as possible. And so if you're getting a bad output, or if your model isn't capable of doing what you're asking it for, you're not thinking, oh, should I be using a bigger model? Should I not? You're just focused on every other part of your stack. After you have your product kind of locked in with that bigger model, then I think is a great place to start experimenting. If you've just been, for example, using Llama 405B because, well, it's the biggest, it's the best one, rather than taking, a couple weeks to set up all of your, optimizations, your speculative decoding, your tensor parallelism, your, multi H100 cluster to try to get this thing to run way faster. Well, first, you should probably go back to those evals like we were talking about earlier and see, hey, maybe 70B is going to do exactly what I need as well. And then I get all those latency and cost benefits out of the box, and then I can go optimize it. So again, at the beginning, working with the biggest, best model is, I think, the absolute right way to do it. And then after that, you can experiment with smaller models. You can also, of course, experiment with fine-tuning smaller models for your domain, for your use case, which we've seen people have a ton of success with, going from a very large, expensive general purpose model to a narrow, fine-tuned small model to get much better latency and cost characteristics.
In terms of that early evaluation cycle of, I'm just going to throw the biggest model I can at the problem, you also run into the limitation of, hey, this model doesn't even fit on my laptop. So I'm wondering how you see folks addressing that hurdle of being able to even just get access to one of these massive models that require multiple GPUs in tandem to be able to even load the thing.
Absolutely. So this is a place where I'm very privileged. I've never had to try and figure out how to put a model on my laptop, except when I've been playing with local inference for fun, because I get to work with GPUs all day, which is a very exciting thing. I think that at this point, there's this blog post that I read a while ago that I think was called something like "The Peace Dividend of the SaaS Wars," that talks about the massive proliferation of free tier developer tools where you can, have an authentication service that'll support 10,000 users for free. You can have free billing. You can have free databases. You can have free, I've been hosting my websites on Vercel and Netlify for years, and I've never paid them a penny. So that sort of peace dividend of the SaaS wars phenomenon is kind of happening as well in the AI space. There's so many different inference providers and platforms that are trying to compete for people's compute workloads, that if you want to experiment with just about any model out there, you're going to be able to find someone who's going to give you some free credits to play around with it. because, the real money in inference is made from mission critical production workloads. It's not made from people playing around. So I think that every platform is trying to, attract that developer audience by giving away that sort of peace dividend, and in doing so, trying to win the inference wars, so to speak.
Another major decision that needs to be made before you can actually put something out in front of your end users is what you're actually trying to solve for. And to that end, you also have to consider what is the overall application architecture that I'm building from. Some of the main ones that I've seen are just throw a giant model at the problem, or the biggest one that's been gaining a lot of attention is RAG, or retrieval augmented generation. You also mentioned fine tuning. And then, as an expansion to all of that, there's also the concept of these multi-agent systems. I'm wondering if you can talk to some of the ways that people need to be thinking about which one or which combination of those architectural approaches they want to consider, and any others that I didn't mention.
Absolutely. So I think that retrieval augmented generation is a example of a broader trend that I'm seeing, and that broader trend is sometimes being called compound AI. It's the general idea that once you're going from that experimentation phase that we've been talking about, where you're just trying to run one model and see what it can do, to a actual product, to an actual production use case, you are probably doing more than just building a ChatGPT wrapper. You're probably just doing more than sending one request to the model and getting it back. So compound AI is the idea that you're going to have multiple models in a single pipeline. You're going to have multiple steps of inference to any given models. You're going to need to add in business logic. You're going to need to add in authentication and routing, conditional execution. We've seen stuff like companies building routers where it'll analyze your query, and then depending on the complexity of the query, send it to either a small model or a large model. All of this sort of stuff needs to get orchestrated in a seamless and most essentially a low latency way. So I've seen a bunch of different tools and techniques around this sort of idea of compound AI. You can look at tools like LangChain as a great example, and some of their agent frameworks as well. And I think that a lot of these, architectures like retrieval augmented generation or, agentic workloads are kind of extensions of this. We're also seeing a lot of stuff with structured output and function calling being very relevant here. Models, if you're going to put a bunch of models in a sequence, then you need to address the reliability issues that they have, because if something's 99% reliable, but then you run it 10 times, well, then it's not 99% reliable, it's 99 to the 10th power, and that's going to be a much lower reliability. So there's a lot that has to be considered when you go into these multi-step pipelines, but it's worth it because, again, like, you're not trying to build ChatGPT wrappers, you're trying to build real applications, and that generally requires more than just a round trip to a single model.
In addition to the model selection, as far as how big or how small to go, and how do I think about the overall architecture of my system, there is also the consideration of the rapid succession of new model generations with new capabilities, the growth of multimodal models. And I'm curious how you have seen that rapid pace of model evolution impact the way that teams think about how to design their overall application, and whether and when to actually engage with this overall space of AI applications.
Yeah, it can be tempting to just kind of wait, because stuff does get better over time. A few months ago, vision was brand new. Most language models couldn't really do vision. Now everyone has vision. Llama has vision. Quen has vision. Everyone has vision. Mistral has vision. And function calling was new. Function calling is the idea that you have specialized tokens within your vocabulary that allow you to select from a set of options and give a sort of recommendation based on a prompt and a set of options. So, you might give it a set of API endpoints with documentation and say, hey, which endpoint should I hit to solve this particular problem? It's very important for building agents. Anyway, so a few months ago, very few models had function calling capabilities. Now, like Llama 3.21b fits on an iPhone, and it has function calling capabilities. So with these rapid advancements, it's pretty tempting to just kind of wait and hope that time solves all of your problems. But once you actually dig in and start using these models, you realize that this stuff doesn't always work super well right out of the box. And that's a good thing. Like, if everything just worked perfectly out of the box, there wouldn't be cool problems for us to solve as AI engineers. But because of that, if you're just kind of waiting around for the models to get better before you start building with them, then once they are good enough, then you're a little behind because you haven't been working with these early versions, learning where there can be pitfalls and learning how to work around them. A great example of this is in the structured output space. So since ChatGPT was released, people have been trying to get it to put out JSON. There was that whole trend a year or so ago of saying, hey, give me JSON or my grandma's going to die. So we've been increasingly, getting better and better tooling for that. Stuff like outlines is a great tool for building more structured output. And if you were to look at stuff like JSON mode today, you would say, oh, wow, this actually isn't that effective because you can't do deeply nested schemas. You can't do, certain conditional fields. And if you don't have that background, then when you look at the drawbacks of something like outlines and you say, hang on, wait, why am I waiting 25 seconds for a state machine to get generated so that it can apply token masks and actually enforce a more complex schema? Well, then you might not understand why those trade-offs are being made and why what we have now is better than what we had a few months ago. So yeah, I would just definitely not be intimidated by the pace of change in the field, because it's a really good opportunity to learn something today with all of its rough edges so that you can be part of the process of smoothing those out and not get, caught on them down the road.
Once you have settled on your model selection, you have your overall architecture and some of the logic built, you also have to tackle the question of the model serving framework. I know that at BaseTen, you've got the truss framework, and you also have chains, which was built on top of that. I'm wondering if you can talk to some of the main entrants in this space of the model serving layer and the role that it plays in the context of the application, and then in particular, how that contrasts with something like a LangChain or a Llama index.
Yeah, so the point of a model serving framework is you have these model weights and you want to go to a Docker image with a API endpoint. And that process of getting there has a bunch of components in the stack. You have a model inference engine, you have a model serving engine, you have certain optimizations that you might be putting in there, you have some sort of model server code, you have your endpoint specification. So this is, BaseTen is certainly not the only company that is trying to work on this. There are a bunch of notable frameworks. There's Ray is a very popular framework that does model serving. MLflow is another popular one. Other startups have, Replicate has Cog. There's Bento ML. So there are a bunch of options for going from, okay, I have some model weights sitting in a Hugging Face repository to, okay, I have a GPU or multiple GPUs that are up and are ready to take traffic and return the output of this model inference. And so, yeah, the role of that is just saying look, me personally, I don't really know Docker super well. Infrastructure is definitely a weakness of mine as a developer, but I can write Python code. I can write a YAML configuration file. I can, understand how to run a TensorRT LLM command to build a serving engine. So all of these frameworks are just designed to take ML engineers, AI engineers, data scientists, who are familiar with more of this like Python tooling and say, hey, let's use the tools that you're familiar with so that you can get good abstractions on top of the ones that you don't work with on a day-to-day basis.
So putting this into maybe web framework terminology, from the way that I'm understanding it, you've got your LangChain or Llama index, which is equivalent to your Flask or Django in the Python world, or your Rails or Sinatra if you're a Ruby person. And then it sounds like the model serving layer is maybe the WSGI.py or the rack application that says this is how you actually load the web service. And then when you get to the actual inference engine, that's analogous to something like a UWSGI or a GUnicorn that's responsible for actually keeping the process running and handling the inputs and outputs.
I think that's a pretty good analogy. The one thing I would add on top of that is the layer that's more about the orchestration of the endpoints. So I would say that the trust server is more like that Django or Fast API thing, and then the LangChain and chains like BaseTen's trust chains and the other products out there for that are kind of a new level that might be more analogous to something like, I mean, it's not really a developer tool, but something like Zapier that's helping you combine multiple API calls together and orchestrate them in like a, DAG type fashion.
And now moving into that inference engine place, I'm wondering if you can share who are the major players in that space? What are the differentiating factors between them? How do people work through that decision process of, do I use VLLM? Do I use the TensorFlow serving or inference engine? Like, what are the options? How do I think about it? And what are the ways that they're trying to compete on features?
The two inference engines that I generally see the most are VLLM, which is a open source serving framework, and TensorRT LLM. TensorRT LLM is built on top of TensorRT. It's by NVIDIA. TensorRT LLM is open source. Parts of TensorRT are also open source. They're both quite good. The difference between the two is VLM is generally easier and it's pretty quick to set up like an OpenAI compatible endpoint for basically any large language model. The downside is that it just can't always match the performance of TensorRT LLM. TensorRT LLM does have a much higher learning curve. It can also be a more restrictive framework in terms of, for example, if you compile a TensorRT LLM engine for a specific GPU, you have to then serve it on that exact GPU. So if I build an engine for an A100 and then I get an H100, well, if I want to serve the model on an H100, I've got to rebuild the engine on that GPU. But the TensorRT LLM does do a great job of super high performance inference because, as a framework by NVIDIA, it does a really good job of accessing the sort of architectural features of the GPU. That's why when we look at, for example, the Ampere versus Hopper architecture, if you look at an A100 versus an H100, the H100 is 30 to 60% more powerful in different dimensions, depending on how you look at it from the raw spec sheet. And, in many cases, you might look at that and put a LLM on it and expect that you may be getting twice that. But when you're running TensorRT LLM on both of them, you're actually going to get more, like in some cases, 3 times the performance from an H100 because it takes those model weights, compiles optimized CUDA instructions for the specific model you're trying to run on the specific hardware you're trying to run it on for the specific, batch size and sequence links and everything about your production workload that you specify to the engine builder. And then it produces that artifact that's, incredibly well optimized for your use case. And TensorRT LLM also has great support for stuff like quantization. You can do post-training quantization as part of that engine building process. Has great support for stuff like LoRa swapping. So they're both really good options. And it comes down to, again, VLLM being a great option that's super well-rounded, and TensorRT LLM being a great option for, the highest possible performance with a little bit more work.
For some of that local on your laptop loop, I've also seen the Llama CPP and OLlama become very popular in that context. is that something that people would generally want to also use in a production environment, or is that generally tuned more towards I just want to use something quickly and easily?
Yeah, generally the latter. So the analogy I like to make, if we're going to be doing web analogies, which I think are very useful, is, a TensorRT LLM and a VLLM are kind of like Postgres or MySQL. They're these productions type databases. And Olama is something more like SQLite. I love SQLite. I use it a bunch for local development and stuff. And there is definitely a niche set of developers who use SQLite very successfully in production for things. So it's not a perfect analogy. But generally, I do think of the Olamas of the world as more of a development tool, while stuff like TensorRT LLM is definitely solely intended for production.
And you also mentioned quantization. I know that that is one of the main ways that people are taking some of these large models and trying to make them more amenable to lower powered hardware. I'm wondering if you can talk to some of the ways to understand the effect that the quantization is having on the model capabilities and performance, and some of the other knobs and levers that people can twist and pull to be able to get more capability out of a model without necessarily having to spring for large, expensive hardware.
There's a lot that you can do on performance optimization. And I think that I generally break it down into two different types of approaches. There's stuff that's kind of generally always good, and there's stuff that has trade-offs. So, going from running just raw transformers on your GPU to running something like VLLM or TensorRT LLM, that's one of those steps that's generally always good. But once you want to start getting better performance than that, you have to start looking at steps with trade-offs. Quantization is the sort of first step that most people take there, and it's a very good one. If any listener wants a quick overview of quantization, models are big matrices. And within that, every weight within the model is a number. Generally, these numbers are in a 16-bit floating point format. So each one is 2 bytes. Quantization is the process of taking those model weights and expressing them in a smaller number format to save space. So you can express it in int8, which is an 8-bit integer, or int4, which is a 4-bit integer. The most recent GPUs from NVIDIA are capable of FP8. So the Lovelace and Hopper series architectures are capable of that. So that's going to be an 8-bit floating point number. The upcoming Blackwell architecture has FP4, which is a 4-bit floating point number. So the advantages of quantization are quite obvious. If your weights are, say, half as big, you're going from FP16 to FP8, then the file is half as big. The amount of VRAM that you need to load the file is half as much. But the bigger, I think, improvement is in your inference speeds. Most of the autoregressive portion of LLM inference, so that's the process of creating the next token iteratively, is going to be bound or bottlenecked by the GPU memory bandwidth. So if your data is half as big, if your model weights and your KV cache and all of these different things that you are processing during inference are each expressed in a number that takes half as many bytes, then the amount of memory bandwidth that is used is much lower. So that sort of addresses that bottleneck. The downside to quantization, because you don't get all this for free, is that you're using a less expressive number format. And so that's why I spent a good deal of time talking about the difference between the integer formats and the floating point formats. The floating point formats are important because they offer a higher dynamic range. So while you still in FP8 only have 256 numbers, they're sort of spread further apart. And this actually matters because model weights, not every model weight is equally important. Just like certain neurons in the human brain receive more traffic, certain weights in the model are, more impactful on the results. That's also why, certain pruning and distillation techniques work, why certain speculative decoding techniques work. We can get to that later. But that is also why the dynamic range of the number format that you're quantizing to matters so much for your model's quality post-quantization. because the more expressive your number format, the more of that model's capabilities you're going to be able to attain. So you can test this using something called perplexity, where you basically you test how surprised the model is by certain sentences, whether or not it would generate those. And generally, you want to see an equivalent perplexity or a very, very small gain in perplexity after quantization. And generally, we're seeing like 99.9% or better perplexity similarities after these quantization processes, and mapping that to something that's indistinguishable to the user. But this can go wrong. I don't know. Tobias, have you ever seen like people on Twitter saying like, ChatGPT is feeling kind of dumb today?
I don't spend a lot of time on Twitter, so I can't say that I have.
Oh, okay. Well, sometimes people say like after a certain update, that certain models start feeling different, and that's because you can definitely have these processes go wrong. So if some shared endpoint provider is under the hood deciding to improve their latency or improve their unit economics by adding quantization or by doing something that's a little bit more cutting edge, something like speculative decoding or pruning or distillation, that can, in some cases, have some effect on output quality. So it's important to sort of understand that the trade-offs exist. And as you go further and further into that applied model performance research space, you definitely need to keep an eye out for, as we said right at the beginning of the podcast, being really good at evaluating your model outputs and making sure that they sort of survive this optimization process.
Once you have a model running in production, you're serving production traffic with it. That also brings in the requirement of being able to understand how well it's doing at serving that traffic, how well it's scaling, what are the error rates, and that brings in the question of monitoring and observability. From a web application or general request response cycle standpoint, metrics and monitoring are a generally well understood subject area. But when it comes to the specifics of working with some of these language models or generative AI models, I'm wondering if there are any nuances to that monitoring best practice or specific metrics that you want to keep an eye out for to be able to understand how and whether and what to do to improve the overall delivery, or cases where you need to be able to scale up, or cases where you need to go back to the drawing board and say, I've got this wrong, I need to start back from scratch.
Absolutely. So once you've solved these sort of model performance problems and you're ready to be in production, you have a whole new set of totally unrelated challenges called distributed infrastructure, which is an entirely different specialization within computer science. And in terms of observability in particular, the infrastructure challenges are not dissimilar to what you would face in serving, web applications. They're just massively magnified by the scale of the hardware that you're using and the models that you're running. So you still care about stuff like requests per second, you care about latency, but that latency is now expressed in stuff like times to first token, total response time, tokens per second, that kind of stuff, rather than just a sort of single end-to-end number. You care a lot about CPU and GPU utilization, you care about your batching, you care about your 400 and 500 error rates, and logs to show what went wrong there. But in general, the infrastructure operations for a large language model or any other generative AI model, if you're going to use it in production, need to have the same level of tooling and the same type of treatment that everything else in DevOps has. So, we've actually been working very hard recently on making all of the metrics available for like export to Grafana and other platforms like that. Because if you have these models as mission critical services within your application, then you need to treat them as such and integrate them into the rest of your sort of observability and reporting stack.
Another aspect of running these systems in production and keeping an eye on their behaviors in the more linear regression or deep learning style machine learning systems, there is the issue of concept drift, where you train the model on a certain set of assumptions, the world changes around it, and so the model predictions are no longer relevant to the context in which they're being provided. I know that there are issues around that with these large language models where they have a certain cutoff as far as past a certain point in time they don't know anything about the world. I know that that has been exemplified by things like asking who is the president of the United States and getting the previous president because time has passed. Retrieval augmented generation is one general approach to addressing that and keeping those models up to date with the state of the world. But I'm wondering, what are some of the ways that that issue of concept drift manifests in the world of generative AI?
Concept drift is, in many cases, if you're doing RAG, more of an engineering problem than it is a AI problem. So it's about making sure you're invalidating your caches, making sure your data is appropriately chunked, making sure it's up to date, that kind of stuff. And that's maybe surprising to someone coming from a data science background, thinking that there must be something wrong with the model, when I've seen so many times on like my docs chat, for example, it just is finding a file I deleted a while ago and isn't busted out of the cache yet. So that's, I think, the biggest difference here in the ML space versus the generative AI space, when we talk about concept drift and stuff, is that if you are observing, strange behavior, and of course, if this is assuming you haven't touched the underlying model weights, you haven't done any of these performance optimizations, these sort of techniques can certainly be to blame for changes in production behavior. But if you're just holding the model constant, then generally a lot of these times it can be more of engineering challenges rather than data science challenges that are causing this concept drift.
In terms of your experience of working in this space, working with customers who are working on getting their models and applications into production, I'm wondering, what are some of the most interesting or innovative or unexpected ways that you've seen teams manage this overall process of going from I have an outcome that I want to achieve with AI to I have actually got this running in production, and their journey from start to finish?
Yeah, I mean, I've seen a bunch of amazing stories, and I think the best ones come from restrictions, because as what's his name, Mark Rosewater, who created Magic the Gathering, likes to say, restrictions breed creativity. So I think a great example is we were working with customers in Australia, and Australia doesn't have H100 GPUs, or at least didn't at the time, with the regions we were looking at, with the data centers that we had access to. And so we learned a lot about how to split very large models over 8 or more A10G GPUs and still get great performance out of it. That's how we learned a lot about stuff like tensor parallelism. We've also faced certain capacity constraints, especially around A100 and H100 GPUs. So we got good at cutting H100 GPUs in half. It turns out that for a lot of things, like, say, serving Llama 8B, you don't need the full 80 gigabytes of an H100. So you can do something called multi-instance GPUs and, quite literally split the GPU in half. And now you have almost two H100s, which, multiplied by entire clusters, can definitely increase your availability. So while these, compute availability restrictions have been a challenge that we've had to overcome, and have overcome through, things like multi-cluster, multi-cloud, multi-hardware platform, the sort of spot solutions that came up in the interim are definitely fun to experience.
In your experience of working in this space, helping customers to achieve their desired outcomes, trying to stay up to speed with the rapidly changing landscape, what are some of the most interesting or unexpected or challenging lessons that you've learned personally?
Kind of like we talked about earlier with the idea of concept drift, thinking maybe it's going to be a model issue and it's actually just that you haven't cleared your cache and it's pulling some old file. A lot of the hardest challenges that I faced have not been AI challenges. They've been the engineering challenges around it. I can think of times when an unpinned dependency or a broken Hugging Face URL or a update to the underlying model has caused weird bugs that I was convinced were some issue with one of the complicated parts of my code, of course, right? Because the complexity must be where the bugs lie, but it's actually something super simple. I do want to acknowledge that just because we're working with these really cool cutting edge models doesn't mean that we're immune from typos and stupid bugs. That said, the fun answer, the podcast answer to this question is I've learned a lot of interesting lessons on nonlinearity, the way that things can both break and also work at unexpected ways at scale. So, like, a great example of the upside here of nonlinearity is something like speculative decoding. So speculative decoding is this performance optimization technique that we've been doing a bunch of work with, where you have a draft model. It's going to be a smaller model, say like Llama 1B, and then you have the target model, which is Llama, say 70B, 405B, some much bigger model. And the idea is that even though this big model is 100 times or more the size of the small model, that it's not going to be 100 times better, or at least like it's not going to work 100 times more often. Maybe the small model is going to be able to get 90% of the way there. So the way that speculative decoding works is the small model creates draft tokens, which are then verified by the large model because the process of verifying these tokens is substantially faster than the process of generating them. And then if the draft model token is wrong, only then does the large model actually generate its own token. This saves a lot on inference time. So that's a great example of where nonlinearity in this space can have great upside. Is, oh, hey, cool, now I'm running this very large model, but most of my tokens are being generated by a much cheaper one. The downside is that it comes and bites you all the time in unexpected ways. So I was doing some benchmarking recently of different batch sizes for LLM inference, and specifically looking at time to first token. And it was steadily increasing with batch size. I've got a batch size of 1. My time to first token is 40 milliseconds. Or I guess technically I was looking at prefill, but prefill is what informs time to first token. Batch size of 2, okay, now it's 50. Batch size of 4, and now it's 75. And it kept going up like that until all of a sudden the batch size was, 96 or something. And it spiked from a couple hundred milliseconds to a couple seconds. I was like, whoa, what's going on here? Turns out that there's only, so much memory available on GPU. And as soon as the batches are large enough that there starts to be collisions during that prefill process, then the latency for time to first token shoots through the roof. And that's effectively a limit on how big of batches you can have at a certain sequence length for a given model. So there's definitely all sorts of things like that. We also saw we got really, really good at cold starts when models were, 5 gigabytes plus the serving image. And then models got 100 times bigger, and we had to re-architect everything because it doesn't just scale linearly. So that's definitely been the biggest lesson I've learned working in the space from an engineering perspective, is if something is going wrong, it's for one of two reasons. Either I made a very stupid engineering mistake, or I ran into a very cool nonlinear problem in AI engineering.
And for people who are considering how they're going to run their AI systems in production, what are the cases where BaseTen is the wrong choice?
That is a great question, and one that I actually have just spent a lot of time looking at because I've been doing some competitive positioning work. So BaseTen offers dedicated deployments. So with BaseTen, you deploy your model and you get this auto-scaling infrastructure, and the whole GPU is yours. So you can put as much batch traffic through it as the GPU could support. And this is great at scale. But if you're just looking to run an off-the-shelf open source model occasionally for side projects and stuff, that's actually not the best approach to this dedicated deployment. What you're probably going to want is a shared inference endpoint. It's going to be easier to use and more cost effective, because you just, instead of paying for minutes of GPU time, you're paying for individual tokens, which are sold by the million, so they must be pretty cheap. There's a bunch of shared inference providers out there. I've been really impressed by providers like Grok that are making their own hardware for this shared inference approach, because you're really getting to benefit from economies of scale with other individual developers who are also running inference through that. So that's definitely an option if you're starting out, if you don't have enough traffic to saturate a single GPU, and if you're not doing something that has like compliance or privacy restrictions, then definitely just throwing it into a shared inference endpoint is a great way to go. And if you're just looking to, experiment on top of the GPU and you want the absolute lowest price per hour for, say, like an H100, you're definitely better off with something like RunPod or Lambda Labs, where you can spin up a bare metal machine and load whatever software you want onto it and experiment from scratch there. So BaseTen is more of a production platform for latency sensitive, mission critical workloads, high throughput, compliance, security, privacy all matter. It's those circumstances when people come to us.
As you continue to invest in this space, stay up to speed with the evolution of the AI industry, what are some of the future trends and technology investments that you're focused on?
I'm definitely keeping a close eye on local inference. I think that when Apple came out with Apple Intelligence a few months ago, there are definitely things to criticize about that announcement. But one thing that I really appreciated and I do think is the future is the way that they kind of blend the on device inference and the cloud inference, where you have certain cases where, for latency or privacy reasons, you can answer certain small queries on the actual end user's device using their built-in compute capability. And then for other things, you're going to have to outsource to a more powerful model running on the cloud. That's definitely an area that I'm keeping a close eye on, and I think is going to have a pretty big impact in the coming years. I'm also just looking at the increasing competition with open source versus proprietary models. Llama 4 is, of course, coming. I personally don't have any insight into when or what it's going to be beyond what's publicly known. But I do assume that there's going to be a good deal more multimodality than in the existing models. We already saw that with 3.2 coming out and having vision capabilities. So that's another thing I'm very excited about and looking for in the future is the mix between taking specialized models for single modalities and assembling them together to build these multimodal pipelines. Like today, you might take a text-to-speech model, you might take a language model and a transcription model, so like Whisper and then Llama and then some like Piper text-to-speech or something, and assemble all three of those together to build a, say, talk to an AI system. And now ChatGPT, or the GPT API, has voice mode, which is a single model that kind of combines all of that together. So I think there are pros and cons to both approaches, and I'm interested to see in the long term how open source foundation models either, or not either, like which models are going to embrace multimodality within a single model and which models are going to try to specialize in doing one modality really, really well.
Are there any other aspects of this overall process of building AI systems, running them in production, and managing those workloads that we didn't discuss yet that you'd like to cover before we close out the show?
I think one thing is the compliance aspect. So we're seeing companies in healthcare, in finance, in other regulated industries. We're seeing governments and educational institutions get really interested in building with OpenAI, get really interested in building with AI, and not just building prototypes or proof of concepts, but building actual production systems that are used at scale. And for these companies, there's another sort of wrinkle in the regulatory and compliance aspect that can affect all sorts of things in the product decision, but also affect a bunch of things at the technical level. One thing that we're seeing a lot of demand for is self-hosted inference and hybrid inference, where the model workloads can be split across multiple VPCs and can be sort of locked to specific regions, locked to specific inference providers, locked to specific public clouds. And so being able to still offer the sort of flexibility and clean developer experience of just kind of spinning up an arbitrary GPU and running it with the restrictions of having a certain region or a certain cloud that you have to operate within is definitely a challenge moving forward that more and more organizations are going to run into.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you and the rest of the BaseTen team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gaps in the tooling, technology, or human training that's available for AI systems today.
That's a great question. I think the biggest gap going back to the beginning is that evaluation. Even when I'm using these models for personal projects or when I'm using them for one-off tasks, all the way to when I'm seeing customers build applications on top of them, the sort of biggest common thread is trying to figure out how to make sure that the model is actually good, which starts with figuring out what actually good means and then systematizing the process of measuring that. There's a ton of people doing really good work in this field. I don't think that it's going to be a gap or a problem forever. But it's something that I'm currently starting to learn a lot more about. And it's something that I think is going to remain a challenge as models scale and the use cases for them change.
All right. Well, thank you very much for taking the time today to join me and to walk us through the process of getting your model into production and all of the different decision points and technology choices that have to be made along the way. It's definitely a very helpful exercise for me, and I'm sure for everybody listening. So I appreciate the time and energy that you and the rest of the BaseTen team are putting into making that last mile piece easier to address and all of the content that you're helping to produce to make that end-to-end process smoother. So thank you again for that, and I hope you enjoy the rest of your day.
Thank you so much. Thank you for having me. Thanks everyone for listening, and I look forward to learning more about all this stuff together.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.